I always found exponential growth and decay to be difficult, so I'm going to try to use as few words as necessary to express the concept as we go, and hopefully that makes it clearer than confusing. The first thing I want to point out is that we remember already that if we have an f of x is e to the x, I'm going to even say e to the ax, some number, then you should remember that f prime of x is also e to the ax, and then with the chain rule you'll have an a out here too. Derivative of the outside, derivative of the inside. I hope you remember that. And that's very important to us because they show us in exponential growth and decay that basically, well, they'll write it this way, dy dt equals ky, like that. Let's make it better, k there. Ky, like that. And this is actually the same thing because here's y, and here's the original times a, so that's going to be our k in this case. It's the same thing, which means that e to the x represents exponential growth. And they definitely find that to be true in banking and population growth. There's a million things we're going to use for examples. Today's first problem is about E. coli. Very common first problem. They tell us that it divides every 20 minutes, and then they tell us that it starts with a population of 60. So we'll use that information, and I like to call it the PERT formula because I write P of t, the population of t. It's a bad P though. P of t is equal to some starting population, which we call P naught, e to the RT. So there's the PERT. And E represents a continuous compounding. We don't need to get into the hardcore math because we're applying calculus right now. And they give us some of the information for this problem. They tell us it starts at 60, so that's our P naught. And they tell us E, it's every 20 minutes. That's 1/3 of an hour, and they're asking about hours here. So I'm going to call it 1/3. Doubles the population, divides into 2, right? So double 60 would be 120. Let's divide the 60 out, and you're going to get, of course, 2 equals e to the r over 3. And now if we want to find r, well, we've been doing it for a couple chapters now. We take the natural log of both sides. Anytime your variable is in the exponent, this is what you do. E to the r over 3 like so. And we do it because it lets you take the exponent and bring it right outside the natural log. It's such a magical function. So we're going to get ln of 2 equals r over 3 ln of e. And natural log of e is equal to 1, so that's just gone, times the 3 up this way, and we're going to get the r, our rate of growth, our rate of continuous compound growth, is 3 ln 2. And in a calculator, that's going to be somewhere around 2.1-ish, but we're just going to keep it as the exact value, which is 3 natural log of 2. Or in French, because it's ln, it's like log naturel or something like that. Now for us, why does that matter? Well, they asked us to find the relative growth rate, so we did that. That's what that is. That's what r is. And then they ask us to find an expression for the number of cells after t hours. Well, that's the PERT formula. So we say P of t is equal to 60, the starting population, times E, and R we now know is 3 ln of 2 times t hours. That's it for part B. This is our magic formula now. And they say find the number of cells after 8 hours for part C. Well, you just put in 8 for that. Right, so you would get 60e to the 24 ln of 2, and I get, and the number is wild. I actually calculated it, so I'm just going to pull it off of my calculator here so I don't get it wrong for you. And I want you to see the actual number. It's 1,006,632,960. It is just over 1 billion cells. In just 8 hours, you go from 60 to 1 billion bacteria. This is real numbers. This is what really happens. This is the actual rate of multiplication of bacteria. It's a humongous rate of growth. Any rate of growth above a small decimal point is pretty powerful. So what do they ask us for next? Find the rate of growth after 8 hours. Now that is not the same as relative growth rate. They want you to find it at an exact time. Guess how you do that? You're going to take the derivative to find the slope at that exact time. So we'll call it p prime of t equals 60. And then what's the derivative of e to the x? It's e to the x. So we're going to do e to the 3 ln of 2 t, and then times chain rule, which is 3 ln of 2. Okay, there's our chain rule part. So 3 times 60, so we're going to get 180 ln of 2 e to the 3 ln of 2 times 8. So maybe we'll back that up and we'll call it e to the 24 ln of 2. And when I put that into the calculator, I get about 2.1 billion. That's crazy. 2.1 billion is the rate of growth at the point where there are a billion bacteria. So you can see at that point, every 20 minutes, you're going to get a lot more bacteria. That's just how it works. So let's back this up a little bit because I want to move to the next part where it says, when will the population, I'm having some compute problems right now, when will the population reach 20,000 cells? Well, population, that goes back to our original PERT formula. So let's bring that in. And we'll say 20,000 equals 60 e to the 3 ln of 2 t. Divide by 60. What's 20,000 divided by 60? We'll call it 1,000 over 3 equals e to the 3 ln of 2 t. Natural log both sides, right? Because it's in the exponent. We've already talked about that. And you've done it a bunch of times, so we'll say ln of 1,000 over 3 equals, and if the ln is here, remember we're going to bring the exponent out, so we'll call it 3 ln of 2 t ln of e, and we'll cross out the ln of e. So we'll take t equals the ln of 1,000 over 3 divided by 3 ln of 2. And that should be, my math says it's somewhere around 2.8 hours. So you see the trick here? When you use one derivative, you can kind of bounce back between the original function and its derivative. There's this guy here and this guy here, to work with each other to find these answers. We're going to have lots of examples of this, so take from what you can from this, make sure that the algebra kind of makes sense to you, and just move to the next one.